So, yesterday we sort of began from scratch and reviewed a good deal of basics of systems of linear equations, matrices and linear maps, and we saw that these three seemingly unrelated things are very closely tied with each other. So, in particular I want to remind you that suppose you have a let me use this. Suppose you have a linear map T from V to W, linear map or linear transformation V and W vector spaces over a field K. As I said, you can think of K as R or C if you find the word field a little abstract. Let us say of dimension n and m respectively, then to that you can associate an m cross n matrix. Okay. Let us say A equal to Aij, which is determined as follows. It is actually determined by a linear map and by choice of basis of the domain and the codomain. With say basis, I do not know, say V1, V2, Vn of V and W1, W2, Wm of W, and this is determined by the equation T of Vj is summation Aij Wi for Ej from 1 to n. Okay. And as I have explained to you that this matrix, so for example, I have this A11, A1n. The columns of this matrix corresponds to coordinates of the action of T on the basis vector. So, T of V1, if it is written as a combination of W1, W2, Wm, then there will be coordinates A11 W1 plus A21 W2 and so on plus AM1 Wm. Then those are the coordinates. So, maybe we can suppose I give this a name. Okay, let me call this I don't know. Okay, let me call this C and D. Okay, so we may denote A by matrix of T with respect to basis of C and D. So, I guess I write the domain basis for the domain here, basis for the codomain here. Okay. So, if you take the standard basis for both, let us say if V and W are Rn and Rm, and you take the standard basis, then you will get the just the linear transformation would just correspond to taking a vector and multiplying it on the left by the corresponding matrix. Okay. So, any linear transformation of finite dimensional vector spaces gives rise to a matrix provided you fix basis, and conversely any matrix would give rise to a linear map of the corresponding vector spaces. Okay. So, a very basic property that I may have stated, but I think it is so important that it is worthwhile. So, let us suppose I have maps. Suppose I have vector spaces, maybe I call it U to V and V to W, and I don't know, maybe I call this F and I call this G, R linear maps of finite dimensional vector spaces UVW of dimension, let us say, I guess I call this n and this m, so maybe I call this p and m respectively, and suppose we fix basis, maybe u1 to up, let's say call it b, b1 to bn, and w1 to wm of uvw respectively. Okay. So now when I have such a map, of course I can cook up a new map which goes from u to w. This is the so called composite. So it is f followed by g. So you the way it comes out is g composed with f. So g composed with f is a map defined from u to w, and its value at some vector u is just g of f of u. And it is clear that if f and g are linear maps, then so is this g composed with f. Okay, or it's better to read this as f followed by g here. Very good. So now the natural question is, I have this linear map, I have this linear map, I have a matrix. So now question. What is the relation between the matrix of say f? So what are the bases here? I guess I called it B, C, D. B here, C here, C here, D here, and G composed with F. What would I have? B here and D here, right? So let us try to figure this out. So we'll keep this thing here, except now maybe what is it? The map from so suppose so there are too many letters. So suppose I write matrix of F with respect to B and C as what shall I call it? Say Fij. What will be the size of this matrix? What's the size of this matrix? Yeah, P cross N. There are so many. There are P, N, M. Make up your mind. F is a map from where to where? U to V. So the size of this matrix will be what? N cross P, right? It's the dimension of the codomain cross dimension of the domain. See, remember T was from V to W, N M, and I get a matrix M cross N. So this will be a matrix of size N cross P, and matrix of G with respect to what are the bases here? C and D. Let us just call it Gij. Okay, so this will be a matrix of size what? Yeah? M by N. Okay. So what does it mean? It means that f of, see, as remember that relation, f of, let us say uj is summation Fij Vi. I going from where to where now? I will go from where to where? 1 to n, and j here will go from 1 to p, and let us say g of vj will be summation, let me just see, okay, g I j w I will go from 1 to m, and here j is going from 1 to n, right? Very good. So these are the defining relations. This is what determines the matrix. The point is that because it's a basis, every vector in that vector space can be expressed as a unique linear combinations. So these Fij's, Gij's, they are uniquely determined. That's why we have to fix a basis. If we use a different basis, we will get different matrix. Okay. So this, I mean, this is computation that everybody should do once in their life. I guess I am doing it more than once, but anyway. So now what do we want to look at? We want to look at the map G F followed by G composed with F. Okay. So in order to understand the matrix of G composed with F with respect to B and D, B is a basis of the domain, D is a basis of the codomain, what should I do? I should look at what happens to G composed with F at a typical basis vector of which space? U, V or W? U. So I must look at this at Uj. What will it be? This is G of F of Uj. F of Uj is let us say maybe yeah. So why not? I going from 1 to n. So do I want to use the same? Okay, we'll see. I going from 1 to n, G of, in fact, maybe I will use a different letter. Let me use, say, K, G of, what is F of Uj? F of Uj is summation F, now this I have called K, J, Vk, correct? Oh, something is wrong. I can either have summation, I mean, okay, maybe I was, let us see, G of F of Uj. So this is G of K going from 1 to n, okay. So very good, because F of Uj is that, right? Okay. Maybe we can fit in one more thing. So that's of course G being a linear map, I can pull it out, and this is K going from 1 to n. F of Kj, remember, is a scalar, it's in K, whereas this is a vector. So this is F of Kj into G of Vk, right, because it's a linear map. Now I can express G of Vk by the second formula, okay. So thus, so G composed with F at Uj will be summation K going from 1 to n, F of Kj, and now G of Vk will be, you can help me, summation, I have not used I, so let us say I going from 1 to m. What will it be? G I K, because I am multiplied by Wi, right? Very good. Now we do what is a birthright of every mathematician or everybody who uses mathematics, namely you can always interchange finite summation, right? So you do that. So I write this I going from 1 to m. Now what is depending on I? So there is Wi, that doesn't depend on k, and then I bring in k here. K going from 1 to n. Let me write it like G I K F K J, like that, correct? What is this? This is like I going from 1 to n, the whatever, did I give a name? Maybe I can give a short name to the matrix. suppose I call this capital F, call this capital G. This is exactly the ijth entry of G times F multiplied by Wi, correct? And this is true for J going from what, 1 to P, because U1, U2, UP, okay? So what does this prove? Thus, the matrix of G composed with F with a basis B for the domain and D for the codomain will be G times F, which is matrix of C and D G into matrix of B and C F. Okay. So therefore, matrix of composite of a linear map is the product of the corresponding matrices, okay, provided you keep track of the basis in this in the correct fashion. Okay. In fact, composition, you see, is a very natural operation. You know, you have two maps with the with the correct with the codomain of this matching up with the domain of this, then you can always define composite. This is what could be simpler than this. On the other hand, when you are first introduced to matrix multiplication, you take this row and multiply by the columns. It's not quite obvious why you should multiply matrices this way. I mean, when it comes to addition, you just add component wise. But with multiplication, it's a complicated looking operation. And well, a good reason why matrix multiplication is the way it is because it behaves nicely with the composition. So in some sense, this even motivates the definition of matrix multiplication. So anyway, so we have just answered this question. So maybe we can keep this matrix BD G composed with F is so one of course corollary of this relation is or maybe I give you a very simple example. If I from V to V is the identity map and B is the basis of V, okay, then the matrix of I, when I take the same basis in the domain and the codomain, what will it be? Because I have to look at I of Vj, but I of Vj is Vj and I am taking the same basis, so that means it is like delta Ij, summation delta Ij Vj. In other words, it is the identity matrix. Say In if n is the dimension of V. Okay. So one consequence of this is a linear map. I don't know F. What was F earlier? Okay, from U to V, let us say U to V of finite dimensional vector spaces is invertible if and only if matrix of say what did I BC is invertible or is non-singular, and in this case for the what would be the matrix of the inverse, say inverse will be from V to U, so let us say C and B will be matrix of F inverse. So I mean, invertibility of linear map as a function it's same thing as the matrix being invertible in the sense of matrix theory, which is as you probably know, is the same thing as saying determinant is non-zero, same thing as saying rank is equal to n, etc. Same thing as saying Ax equal to 0 has only the trivial solution, Ax equal to b has a unique solution, etc. Okay? Very good. Why does this follow? Because f, I have map u to v f, and I can take f inverse. If f is invertible, then this is a map from v to u, and if I have a basis b here, c here, again b here, and this composite, of course, if it is invertible, this composite is identity. So that would imply that matrix of so what is it? So matrix of identity, which is the composite from what is it, b to b, u to u, will be the matrix of f in f inverse followed by f. Am I right? No. F followed by f inverse, which is by, and bb here, which is by our formula would be matrix of cb f inverse into matrix of bc f, by what we just established. Okay, I hope my subscripts superscripts are correct. You can check. So, but this is identity, and that proves that this guy is invertible and its inverse is this. Incidentally, it's an elementary exercise that in the matrices, if A times B is identity, that's enough for A to be invertible. Generally speaking, you should have AB equal to identity and BA equal to identity. But if you have one relation, the other becomes automatic. That's because AB equal to identity does imply that A is invertible. For example, using determinants, but there are other ways. So, and then you can play with that inverse. Anyway, this is a very, very basic thing, but it's useful to be clear about it. So, invertible linear maps and non-singular matrices are one and the same thing. And now I want to look at a special case. You notice also that I have a, suppose I have a map, all right, let's say I have a map u to v, okay, and I take some basis here b and c, and suppose I were to take other bases b prime and c prime, okay, then for the same map I will get different matrices, okay. Here I may get one matrix and here I may get another matrix, say capital F and capital F prime. What is the relation between these two matrices? That also follows from what we just showed. Okay, so all right, so let's suppose F from u to v is a linear map. Consider basis b c of u and v, and also and basis b prime c prime also of u and v. Then how do I describe the relation between matrix of F with respect to BC and matrix B dash C dash? So what you do is, I have this map u to v. Okay, here I work with the basis b and c, and I also have the same map F u to v where I work with the basis b prime and c prime, and I want to see what is the relation between these two. So what I can do is, for example, I want to get this map. Of course, it's the same map. I can take the identity map here, follow it with F, and take the identity map here. Okay, except that I work with different bases. So it is true that the matrix of identity map is the identity matrix, provided you take the same basis for domain and codomain. If you did not, then it will not be the same map. But by the corollary, we proved identity, of course, is invertible, So, the matrix whatever it is will be invertible. If I have different bases for domain and codomain and identity map, then the corresponding matrix will be invertible. So, what this relation for example will tell you, okay, so it is slightly, so what will this tell me? So, if I want to look at B prime and C prime of f, so that will be, what is it? Okay, so now you can help me. So, if you like, so it is this followed by this followed by this. So, matrix of B prime B identity composed with matrix of B C F, so not composed, multiplied by matrix of, what is it? This map C prime identity, right? And this is exactly the relation that I was talking about yesterday when I mentioned equivalence of matrices, because this map is invertible, so this matrix is invertible. So, this is of the type, let us say Q F P, where Q and P are non-singular matrices. Okay. In other words, these two matrices are equivalent to each other. These two matrices are equivalent if one can be obtained by another upon pre-multiplication and post-multiplication by non-singular matrices of appropriate sizes, right. So, equivalence of relation is same thing as considering a change of basis at the level of linear map from one vector space to another. Okay. So, is that clear? This is maybe a little bit abstract, but on the other hand it's really a basic fact. So, like I said, if something is not clear, you stop and ask me questions. Okay. So, now we can come to the important special case that we want to do. Special case where I take u equal to v and b equal to c. Okay. So, thus we have a linear map f from let us say v to v now, v is our favorite notation, and a basis b of v, say, and if dimension of v is n, then what? Then the matrix of B F, okay, is n cross n matrix. Okay, let us say A determined by f of Vj is summation Aij Vi, I going from 1 to n, and j is also going from 1 to n, because I am looking at m equal to n. It is a square matrix. Okay. Further, if I look at matrix of the same map, but with respect to another basis, b dash and b dash, if b dash is another basis of V, then matrix of F with respect to that, what is the relation? We have the general thing here. Okay. So, I just have to change C to B, keep the dashes, right. So, it will be M B B dash I M B B F M B dash B I, right, where I is the identity map. In particular, I is invertible, and hence the matrix of I, which is this. So, let me call it say B dash B, let me call it P, is non-singular, right, because map is invertible if and only if its matrix is non-singular, no matter what basis I take. Okay. And furthermore, if I look at this matrix, what will be its inverse? The map is I only, but the basis will get interchange, right, because it is going from the codomain to domain. So, it will be this B dash B will be swapped to B B dash, and P inverse is matrix of B B dash I. Everything follows from this composite relation and its corollary. So, it's an important thing to derive. Okay. So, what is the upshot then? The upshot is thus let us call it A dash to be the matrix of F with respect to B dash is related to A, which was matrix of A with respect to B, by the relation that A dash is equal to, so I call this A, I call this P, and this becomes P inverse AP. Okay. So, this is called the relation of similarity. Okay. So, definition, in other words, A is similar to A dash. We write it in symbol as A similar to A dash. Very good. Notice one so maybe remark. So, in general, two n cross n matrices A B are similar if B is equal to P inverse AP for some non-singular matrix P, of course non-singular n cross n matrix P. Okay. You can check that. So, what we have just shown is that similarity is sort of change of basis corresponds to similarity. The converse is also true, that if I take a matrix, okay, and it defines a linear map, and if I take a matrix which is similar to that, then it would correspond to the same linear map, okay, and this would accept A is a n cross n matrix over K, and A dash is similar to A then the corresponding linear maps how shall I say this? So, are essentially the same. So, okay. I can make it more precise, but what I want to sort of basically drive home the message is that similarity of matrices corresponds to change of basis. When you have a linear map, okay, and then you can, of course, the matrix corresponding to it is unique provided you fix basis. If you change your basis, then the matrix that you would get is similar. Okay, so I think that's the main take home message. So just like equivalence of matrices B equal to QAP is a equivalence relation on the set of rectangular matrices, similarity is also an equivalence relation on the set of square matrices. Everybody understands what is an equivalence relation? Yeah. I already told you, if you don't know something, or you can always stop and ask, and if I know, I will tell. Okay, so that's the moral. Change of basis corresponds to. In school books, after every story, there used to be a moral of the story. So this is the moral of that story. Okay, change of basis corresponds to similarity of matrices, square matrices, of course. So, so one general problem is to classify matrices up to similarity. What that means is that maybe suppose this is the collection of matrices, then I sort of divide it into some disjoint parts, so that between any two region matrices here are similar between each of these components. There may be finitely many, there may be infinitely many, but no two matrices in different blocks are similar to each other. Okay, and for example, we did this when we talked about equivalence of matrices, and there we saw that one way to recognize whether or not two matrices are equivalent is to simply look at their rank. If the rank is the same, they are equivalent. If they are not the same, they are not equivalent. Furthermore, we had a very nice canonical form for, or that is to say, a good representative for each of the blocks, so to speak. And that block, so for example, we showed that every m cross n matrix is equivalent to something like identity of some size, and then the zeros everywhere, blocks of zeros. Okay, so there were finitely many sort of blocks which divided the space of rectangular matrices up to equivalence. And now one wants to try and understand what is the story when it comes to similarity, and the space is the space of square matrices. Okay, and preferably also try and find good representatives for each of the blocks. So, and it's like, and this is of course is always kind of manageable. I mean, for example, you have India and you divide it into various states, and then you want to say also maybe assign maybe who is a typical Maharashtrian, typical Gujarati, typical Punjabi, whatever. That's so one way to try and do that is to think, look at. So it helps to understand similarity invariants. That means things associated to matrices which remain the same if the two matrices are similar. Let me give you an example. Determinant is a similarity invariant. Why? Because if say A dash is similar to A, then it is clear that determinant of A dash is determinant of A. A dash is like P inverse AP, and that is determinant of product is product of determinants. It's one of the miracles in life. That is therefore determinant of P inverse into determinant of A into determinant of P, but determinant of P inverse is the reciprocal of determinant of P, so the determinants are the same. Some other similarity invariants, you can check what is called the trace is also a similarity invariant. Okay. Trace is what? The sum of the diagonal entries. Okay. You can just do it by direct checking. But of course, this direct checking you can be slightly smart. Instead of showing that trace of A dash is same as trace of A, what you can show is that trace of A times P is same as trace of P times A. So, trace, although matrices don't commute, but if the traces, when you interchange the order, remains the same. That's easy to verify by definition. So, but these are not, these don't characterize, okay. It can happen that two matrices have the same determinant, but they are not similar. Likewise, they can have the same trace, they are not similar. In fact, both the things can be same and they are not similar. Okay, so now that brings us to the following fundamental definition. So here let A be an, okay, I may not say it every time, n cross n matrix over K. Over K means entries in K or field K. Think of K as R or C if you like. Okay. So you say lambda, some scalar, is said to be an eigenvalue of A if A times V is lambda times V for some V in Kn, V not equal to 0. So if there exists a non-zero vector such that action of multiplication by A on the left just corresponds to scalar multiple of lambda, and there are it is known by various different names, eigenvalues, some people call it proper value, some people call it characteristic value, latent root. In English old books they use the word latent. Latent, I guess, means something hidden. So this is this eigen thing. Eigenvalue is really a how shall I say this in, it's kind of a bastardized word, meaning eigen is a German word and value is English, but and you combine the two. But yeah, characteristic value is English. Anyway, I don't think the French use eigenvalue. They use okay. Similarly, if I have a map T V to V, a linear map, and lambda is an eigenvalue of T, if T of V is lambda V for some V in V, V not equal to 0. Okay. So, any such V is called an eigenvector of A corresponding to the eigenvalue lambda, and similarly for a linear map. I mean, of course, the earlier moral was the linear maps and matrices are essentially the same. So, these two things go parallel. I may perhaps even depending on the whim either say this or that. Okay, very good question. How does one find eigenvalues and what are the eigenvalues, etc. Okay. So, that is relatively easy. So, how to find eigenvalues? Are there finitely many? Are there infinitely many? Well, you observe that lambda is an eigenvalue of A if and only if so A minus lambda I, or say let us say lambda I minus A of V is equal to 0 for some V not equal to 0, right. What does that mean? Now, this is a square matrix. I is an identity matrix or identity operator. So, that means this has a non-trivial element in its kernel, okay. Or if the solution space of the corresponding system of homogeneous linear equation has a non-trivial solution. When does that happen? That happens if and only if determinant is 0. So, this is if and only if determinant by what we discussed yesterday. Okay. So, therefore, thus we can consider the polynomial, let us say determinant of x I minus a, let me denote it by chi sub a of x. What is it? This is the determinant of the matrix. So, x minus a11 minus a12 minus a1n etc. minus an1 minus an2 x minus if so this is a polynomial of the type x to the n. In fact, the terms, let us say minus c1 x to the n. Okay, let us just put plus cn. Okay. Are scalars. So, this polynomial, this is called a, so this is a monic polynomial of degree equal to the size of the matrix. This is called characteristic polynomial of A. Okay. And you see that are precisely the roots in K of the characteristic polynomial chi Ax. Okay. In particular, because it is a monic polynomial, monic means leading coefficient is 1. In particular, it is a non-zero polynomial. In particular, A has at most n eigenvalues in K, right, because a polynomial of degree n over a field has at most n roots in that field. Yeah. In the special case, in case this field is the field of complex numbers, or more generally, for those of you who know what that means, if K is algebraically closed, then A has, or let me put it this way, chi A x has not just at most n, but in fact exactly n roots, provided we count the roots properly, counting multiplicities. That is to say chi A x will split as maybe x minus lambda 1, say maybe to the power e1, x minus lambda 2 to the power e2, x minus lambda r maybe to the power er, where lambda 1 to lambda r are distinct, and e1 to er are positive integers. Okay. So one calls so in this case lambda 1 to lambda r are the only distinct eigenvalues of A, and this EI, the exponent E1 to ER are called their algebraic multiplicities. Okay, note that the sum of the algebraic multiplicity is the size of the matrix of the degree of characteristic polynomial is n. Okay, so algebraic multiplicity of the eigenvalue is the multiplicity with which it occurs as a root of the characteristic polynomial. Okay, that's the there is also another multiplicity. So the definition called the geometric multiplicity. The of an eigenvalue lambda of A is defined as the dimension of, let me call it E lambda, where E lambda is the set of all vectors V Kn or V as the case may be, so that A times V is lambda times V. Okay, so you look at all possible eigenvectors and put 0 in it also. Here I am allowing V to be 0, and that collection will obviously form a subspace of Kn. Or in the case of linear operators, it will be set of those V in V, so that TV is lambda V for in case of Okay, so this is called the eigenspace. I don't know, eigenspace of lambda or eigenspace of A with respect to lambda, corresponding to lambda. Okay, it's clear that it's a subspace, because suppose I V and V dash are there, then AV plus AV dash will be lambda V plus lambda V dash, etc. And so therefore V plus V dash will also be there, and so on, and any scalar multiple of V will be there. So it's a general fact, not at all difficult to prove, that the geometric multiplicity of lambda is less than or equal to the algebraic multiplicity. How does one prove this, by the way? Maybe I am running slightly out of time, so I may not write down in detail how one proves it. Again, whatever I explained, that change of base, I mean this matrix of a linear map, etc., that will be useful. Okay, you think about it. I will come back to this question. How does one prove this? It's not immediately obvious, but let's look at some examples. Examples of matrices where I want to find eigenvalues. So the simplest example is A is a matrix which has only the diagonal entries. Okay, sometimes we write it diagonal. What are the eigenvalues? There you just see them right there, the lambda 1 to lambda n, because the eigenvalues. These may or may not be distinct. Since, for example, one way to say this would be the characteristic polynomial would be x minus lambda 1 to x minus lambda. The determinant of the matrix which will have x minus lambda 1 on the diagonal x minus lambda 2, etc., and 0 everywhere else. More generally, if A is a triangular matrix, that means upper triangular or lower triangular, okay, then eigenvalues of A are its diagonal entries. So these are examples where it is easy to find eigenvalues. These are because the determinant is just the product of the diagonal entries. Okay. Another important thing to remember is that this characteristic polynomial so I could give you more examples of numerical kind, but any example that I would, okay, let me give you one more example. Serious examples you can do using computer, and that may be done in the lab session and so on. So suppose I have a matrix 0 1 0 0. Okay, what are the eigenvalues of this? 0 0, because it's a triangular matrix. 0 with algebraic multiplicity. Okay, what is the geometric multiplicity? How do I calculate the geometric multiplicity? I look at the eigenspace. So I look at the set of all V such that AV is 0. Okay, so this V may look like, this is a column vector, so it's like I want to solve 0 1 0 0 x1 x2. So I am putting 0 here because 0 is the eigenvalue, is equal to 0 times x1 x2. That is the equation that I want to solve. Okay, so what does that give me? That gives me, so when I multiply this, I get x2 equal to 0, and then the second equation will be 0 equal to 0. So that means any solution of this is of the form x1 0. Okay, so this eigenspace therefore is the span of E1, the first standard basis vector. Is that clear? Any scalar multiple of this. So in particular, so what is the geometric multiplicity then? 1. Okay, as you can see, 1 is of course less equal to 2, but they are not equal in this example. Okay. Is that if say a dash is similar to a, then the characteristic polynomial are equal. Okay, this is kind of straightforward because what is the characteristic polynomial? This is the determinant of I call it xi minus a dash. So, but a dash is similar to a, so this will be determinant of xi minus p inverse AP, and I write I as p inverse p. Okay, then I will be able to write this as determinant of p inverse into xi minus a into p. Okay, which is determinant of p inverse into this into determinant of this, and that is therefore determinant of xi minus a. So characteristic polynomial is a similarity invariant, which means similar matrices have the same eigenvalue, and moreover these eigenvalues will have the same algebraic multiplicity and they would have the same geometric multiplicities. Are the eigenspaces the same? Suppose, so that means if lambda is an eigenvalue of a, then lambda will also be an eigenvalue of a dash. Is it true that if v is an eigenvector of a corresponding to lambda, then v is also an eigenvector of a corresponding of a dash? Then what is the relation? Similar matrices have the same So this is one important reason why eigenvalues are there. Eigenvectors are the same. Then why did you say geometric multiplicity is the same? So we can just check, right? If suppose v is an eigenvector, that means what? Av is lambda v. Now a dash is what? P inverse AP. If I take a dash v, I will get P inverse AP v, and I don't know what is PV. Okay. Instead, what I can do is I can look at a dash acting on P inverse v. What will that be? Now I have P inverse v, so that will be P inverse AV, because P inverse is identity, and AV is lambda v, and lambda is a scalar, so this is lambda P inverse v. Okay. So that will imply that. So so therefore, what does that show is that a v is an eigenvector of A if and only P inverse v is an eigenvector of A dash. So the map v going to P inverse v gives an isomorphism. So here I call the eigenspace of say E lambda A onto E lambda A dash. In particular, isomorphism meaning invertible linear map. 1 1 onto etc. In particular, the geometric multiplicity of lambda as an eigenvalue of A is same thing as the geometric multiplicity. Lambda is an eigenvalue of A dash. Okay. Now, therefore, now of course, so our simple example was that diagonal matrices very easy to find eigenvalues, or triangular matrices very easy to find eigenvalues, and then we made observation that similar matrices have the same value eigenvalue. So, natural question is every matrix similar to a diagonal matrix? That would be wonderful, because then I would find the eigenvalues easily. So, it turns out that that is not true. Why is that? Because suppose A were similar to an suppose every matrix were similar to a diagonal matrix. Well, look at this example, this matrix here. Suppose this were similar to a diagonal matrix. Okay. So, suppose something with lambda 1, lambda 2 on the diagonal. Then for that diagonal matrix, the eigenvalues are going to be lambda 1 and lambda 2. But the eigenvalues of this and that matrix similar to it must be the same. So, those lambda 1 must be 0 and lambda 2 must be 0. 0 are the only eigenvalues. Okay. So, but then that would mean this matrix is similar to the 0 matrix. It's like, so 0 equal to P inverse A P, right, which means A is, but then that would force A to be 0, but A is not the 0 matrix. Okay. So, this is a question. Is every square matrix similar to a diagonal matrix? Answer: for example, consider A to be this. Then if A were similar to, say, diagonal, then we must have equal to 0. But then A is similar to the 0 matrix, if you like, which implies the only matrix similar to the 0 matrix has to be 0. Okay. 0 is in a similarity class by itself. Likewise, any matrix which is similar to the identity matrix has to be identity. Okay. Which is a contradiction, because it has a non-zero entity. By the way, some of you are young faculty. I think this is a favorite question in many faculty interviews. Is every matrix diagonalizable? And if people say no, then maybe sometimes the next question is, how about over complex numbers? And then many people are inclined to think that, oh, maybe over complex numbers it is true. But as this example shows, it doesn't matter. Even if you are over complex numbers, not every matrix is diagonalizable. And these are examples. This is an example of what is called a nilpotent matrix, but you can construct many such examples. So, but of course, being similar to a diagonal matrix is nice, so we make a definition. An n cross n matrix A is said to be diagonalizable, and depending on where you are, this is spelled with a Z or a S. Okay. If A is similar to a diagonal matrix. Is a diagonal matrix for some non-singular matrix B. So, natural question, which matrices are diagonalizable? We have already seen that not every matrix is diagonalizable, but there is but on the other hand, it turns out that lots and lots of matrices are diagonalizable. In fact, the collection of diagonal matrices is significantly larger than the collection than the collection of non-diagonal matrices. You can make this precise in various ways, Lebesgue measure and Zariski topology, etc. But let me just say that lots of matrices are diagonalizable. Okay, so it's useful to know when a matrix is diagonalizable. An easy characterization. So I let then A is diagonalizable if and only if Kn has a basis of eigenvectors of A. Okay. So this is more or less tautological. How does one see that? That suppose A were diagonalizable, that means it is similar to a diagonal matrix. Okay. So that means, so A, of course, A corresponds to a map, say T from Kn to Kn, and A is, let us say, maybe the matrix of this with respect to the standard basis. Okay. So if it is similar to a diagonal matrix, that means there exists a basis V1, V2, Vn, so that with respect to that basis, the matrix is a diagonal matrix, right? What does that mean? That means I have, so if A is diagonalizable, I guess I also use S sometimes then, maybe I call it TA, then there is a basis V1, V2, Vn of Kn such that matrix of, or maybe call it B, matrix of T with respect to B is diagonal, right? That means what? I have lambda 1, lambda n and 0 elsewhere. But remember what I told you about matrix of a linear map? The columns correspond to action on the basis element. So the first column is T of V1, the last column is T of Vn. So, and that is expressed in the, these are the coordinates in terms of V1, V2, Vn. So this means T of Vi or T of Vj is what? Lambda j Vj. And Vj being basis vectors, they are obviously non-zero, they are linearly independent. So that means lambda j is an eigenvalue and Vj is an eigenvector, and you have a basis of eigenvectors. Conversely, if you had a basis of eigenvectors, let us say V1, V2, Vn, and they are eigenvectors, you look at the matrix of T with respect to that. And by what I have explained to you, that matrix is necessarily a diagonal matrix like this. Okay. So that is why I said this is almost tautological if you understand the relation between matrices and linear maps. Okay.
So we can say if you have got a distinct eigenvector.
No.
No, or either algebraic multiplicity.
I will come to that. So So, you see distinct eigenvalues may not be the case.
AM equal to GM is.
That is also correct, that is correct, provided K is complex numbers or algebraically closed. Okay, so I will come to that. So, because you see, for example, identity matrix is diagonalizable. Of course, it does not have distinct eigenvalues, but it is in fact a diagonal matrix, right?
No, like
But it is a necessary, I mean, it is a,
not a distinct eigenvalue, then algebraic multiplicity is equal to.
that is correct, that is correct. Okay. So, this other, so other characterization, except that for that I should have then A is diagonalizable if and only if algebraic multiplicity lambda for every eigenvalue lambda of A. But I must allow myself complex eigenvalues. See, for example, if there are, suppose a K is reals, and it just so happens that my characteristic polynomial is like whatever x square plus 1 whole thing to the power 100. It does not have a real root. Okay. So, then a statement like this will be vacuously true for every eigenvalue, because then I am looking only in that field. Okay. But then this matrix may or may not be diagonalizable. Okay. So, if you have eigenvalues, so for example, if K is complex numbers, then it is okay. And the proof is obvious, because suppose this happens, so this actually, so another, so more, perhaps this number 2 I should have said first. If A has, say, n distinct eigenvalues, then A is diagonalizable. The converse is not true. If A is diagonalizable, does not mean it has distinct eigenvalues. For example, you can take A to be identity. It is diagonalizable, but it does not have distinct eigenvalues. Why is this true? This follows since eigenvectors corresponding to distinct eigenvalues are linearly independent, right? So, correct. So, if you take suppose lambda 1, lambda 2, lambda r are distinct, and you take V1, V2, Vr are eigenvectors corresponding to them, then they are necessarily linearly independent. How does one prove this? You can induct on R, for example. If R is just 1, then you have only one eigenvector V1, which is by definition non-zero. So, that is linearly independent. Suppose it is true for smaller values, suppose R is bigger than 1, and your result is true for say R minus 1 eigenvectors. Then what do you do? Suppose you have this V1, V2, Vr, and suppose they satisfy some relation, say maybe C1 V1 plus CR Vr equal to 0. Then on the one hand I can apply the matrix A to this, and I will get C1 lambda 1 V1 plus C2 lambda 2 V2 plus CR lambda R Vr is 0. That is one relation I get. Or and then I can, for example, multiply whole thing by, I don't know, lambda 1, let us say C1 lambda 1 V1 plus C2 also lambda 1 V1 plus CR lambda 1 Vr, that is 0. I am just multiplying throughout by lambda 1. Then I subtract this from this. I would get, sorry, here V2. What would I get? I would get this I would get a relation between V2 to Vr of the form, because this will cancel. So, I will get C2 lambda 2 minus lambda 1 V2 plus CR lambda r minus lambda 1 VR is 0. So, now I have only r minus 1 eigenvectors. They are also corresponding to distinct eigenvalues. So, by induction hypothesis, that will imply that Ci lambda I minus lambda 1 is 0 for all I from 2 to r. But they are distinct. So, this is non-zero. So, I must have Ci is 0 for all I equal to 2 to r. So, in my original relation, all these guys are 0. So, I am just left with C1 V1 equal to 0. But V1 is not 0, so that forces C1 also 0. So, this also forces C1 equal to 0. So, that proves that eigenvectors corresponding to distinct eigenvalues are linearly independent. Once you have that, then that follows, because suppose I have n distinct eigenvalues, then the corresponding eigenvectors there are n of them, they must be linearly independent, but my vector space is of dimension n. So, if I have a set containing n linearly independent vectors, that must be a basis. So, your vector space has a basis of n eigenvectors, and therefore, the matrix is diagonalizable. Okay. I must spend too much time on linear algebra. I must come to differential equations, otherwise. So, let's talk. Okay, so what is one of the simplest differential equation in the world? So, now my x is a function of t, time parameter. Okay. So, I am sure, so one of the simplest equation is, let us say dx by dt is a times x, right. What is the solution of this? Everybody knows this, I suppose. A particular solution is xt is equal to e to the power at, or a constant times e to the power at, some c, okay. And that constant will be determined if I am also given some initial condition. So, x0 is some, I do not know, let's just say c, why not, x of time t equal to 0, the value is c. Is that correct? Yeah, because I put t equal to 0, I get c. Yeah. So, xt has the unique solution xt equal to c. But now suppose I want to look at, now suppose I have a system, now suppose consider a system, what is called system of linear first order ordinary differential equations of the form. So, I have n functions. So, dx1 by dt is, I do not know, maybe a11 x1 plus a1n xn and so on, and maybe dxn by dt is an1 x1 plus ann xn. If this system was kind of what they call uncoupled, that means suppose I just had a11 x1 here and I had some constant times x2 here, I had a constant times xn here, then it is really the n equations of this type, and I would get solutions very easily by some constant times exponential. But now x1 x2 are mixed. So, how do you handle that? So, first of all, you can write this in matrix form. So, let me write this dx bar by dt equal to a times x bar t. So, x bar t for me is the vector of functions x1 t to xn t. Sometimes I also write this as x dash or just x dash, let us say. So, x dash is equal to ax, where x is now a vector. In books they will write it in boldface. So, I will just write a bar below. Okay. Now, how to solve this? So, this is what we have just learned can help very much. So how to solve? Okay. So, what you do is the following. Consider, A is of course Aij, okay, and for simplicity I am assuming that these Aij's are constants, okay. So it is a scalar matrix, okay. So the recipe for this, which works in many cases though not all, is the following: check if A is diagonalizable, and we will see how we do that, okay. You check and you kind of pray, okay, let us hope A is diagonalizable, and if your prayers are answered, which 99% of the time they will be, I mean it is an infinite sample space, but since most matrices are diagonalizable, then find the eigenvectors, eigenvalues, say lambda 1 to lambda n of A, not necessarily distinct, and eigenvectors, or let us say linearly independent eigenvectors V1, V2, Vn corresponding to these, okay. So that, so by the way, if you are able to do that, then it's a easily verifiable fact that if P is the n cross n matrix whose columns are given by these eigenvectors, these linearly independent eigenvectors, okay, then P is non-singular because these columns are linearly independent, and P inverse AP is the diagonal matrix, is diagonal lambda 1 to lambda n, okay. That's kind of easy to see, huh? Because it's more or less comes from the definition. So you see, because what does this mean? This relation will mean that, suppose I call this diagonal matrix D. So what you are sort of saying is AP is equal to PD, right? So what is AP? How do I check this relation? I check that the columns match up. As I explained to you, how do I find the jth column? I just look at the action on the jth standard basis vector. So this should be DEJ for all j. But this is the jth column. What is the jth column? That's AVJ. But Vj was an eigenvector corresponding to lambda j. So that's lambda j Vj. On the other hand, what is this DEJ? Well, that's lambda j EJ. And so then lambda j is a scalar, so that will be lambda j PEJ. PEJ is the jth column of P. So that's jth column of P is Vj. So as you can see that this is also lambda j Vj, and so is this. So therefore AP equal to PD. In other words, P inverse AP is equal to D. Okay, very good. And all right. So now, so that's the next step. So this is algebra. This is where the hard work is being done. Now you reap the benefits of that. So yeah, now what do you do? So now make the substitution. This x equal to P inverse y, or which is same thing as y is equal to Px. Okay. So I hope this is right. Yeah. Then what happens to the differential equations? Then if you like this dy by dt, which is of course the vector dy1 by dt, dyn by dt. Okay, see this is a column vector this of functions. This will be a new column vector of functions. Okay, what will that be? So this will become, so dy by dt will be, or let me put it this way. So I had originally dx by dt is equal to ax, isn't it? So dx by dt will become, if I am not mistaken, P inverse dy by dt. On the other hand, what is this A? A is P d P inverse of x, correct? Okay. Sorry, I was worried. I think I make the substitution x equal to py, okay, or y is equal to p inverse x. So I will get p dy by dt is equal to this. I need to substitute again for x. So that would imply that dy by dt is p inverse a, and for x I substitute py, right? So that becomes dy, and now this is uncoupled, because this is like dy1 by dt is lambda 1 y1 dyn by dt is lambda ny, correct? That's what the relation is. So the solution by the whatever this 11th standard formula would be given by, so thus y equal to, how shall I say this? So let's say y1 0 e to the lambda 1 t, yn 0 e to the lambda n t, right, is a solution, is the solution, correct? So let's translate that. So y was what? P inverse x. So I get P inverse x becomes, so let me write this as e to the lambda 1 t e to the lambda n t on the diagonal, and maybe the initial value y1 0 to yn 0. Okay. Suppose I call this matrix dt. Okay. So P inverse xt is, so that means this is dt and y is P inverse x0, right? So I get, thus I get that xt is equal to P, because now I multiply by P, dt P inverse multiplied by x0. So that's your solution of the system of linear differential equation, which you get basically by diagonalizing the matrix A. Okay. Now, and so actually you are doing a little bit more. Not only you are sort of checking if the matrix A is diagonalizable and finding the eigenvalues, you are also finding a basis of eigenvectors. By the way, how do you find a basis of eigenvectors? To find eigenvector, you find eigenvalues, say if you are lucky, you can find the roots of the characteristic polynomial. There, by the way, you are not, it's not so easy in general. If I give you some polynomial of degree 100, it's not easy to find out its roots. But in all textbooks, they will give you examples whose roots can be found. And computer can help you a little bit more. But then suppose you do find the roots. Okay, let's say you have the roots lambda 1, lambda n. Now you want to find a basis of eigenvectors. So essentially then you will be solving the system, say you have some root lambda. You are looking at Ax equal to lambda x, or A minus lambda x equal to 0. Okay. So you are solving a system of homogeneous linear equations, and you are finding solutions of that. But you should, and what you probably need is not just one solution, but you want to find a basis of solutions. How do you do that? Yesterday's lecture, use Gauss elimination, or also what Harish I guess talked about in the morning. So you have this, now the coefficient matrix is something like A minus lambda I or lambda I minus A, doesn't matter, and you look at the corresponding homogeneous equation. That means you take that matrix, reduce it to row echelon form, and then whatever is the rank, the number of variables minus the rank would be the dimension of the solution space, and from Gaussian elimination you can also read off the solution of a basis of the solution space. Okay. So that gives you your linearly independent eigenvectors for the eigenspace corresponding to that particular eigenvalue. So you do it for each of the eigenvalues. So in other words, then if you, and your matrix is diagonalizable, so first eigenvalue has some G1 linearly independent eigenvector, second has G2, the rth one has GR. So your geometric multiplicity then will be equal to the algebraic multiplicity, and they will add up to n. So that way you get a basis of eigenvectors. That's where the hard work is in some sense. Once you do that, now you have to do this substitution, etc. Okay. I think I could not get to it, and also I am not an expert really, but Professor Sachin Patwardhan will probably explain to you how the nature of eigenvalues reflects on the solution, what is called the phase portrait and such things, etc. Also, I have to just, if you allow me 2 or 3 more minutes, end with a quick remark, which is that we have seen that not every matrix is diagonalizable. So what do you do in the cases when the matrix is not diagonalizable? Well, then there, suppose again let's continue to assume that we are over complex numbers, okay, or algebraically closed field. Then it turns out that although not every matrix is similar to a diagonal matrix, it can be similar to a matrix in a particularly nice form. So that is called the Jordan canonical form or Jordan normal form. So what it is basically a Jordan canonical form would be something like J lambda 1, J lambda 2, J lambda r, where these are what are called Jordan blocks. And the Jordan blocks, they are kind of model after that simple example I gave you of non-diagonalizable matrices. So Jordan block would typically look like I have some lambda same value on the diagonal, and I have 1 on the super diagonal, and I have 0 elsewhere. Okay. These are typical examples of non-diagonalizable matrices, because if this were diagonalizable, it would have to be lambda times identity, but it is not. You have this 1 on the super diagonal. Okay. So, but you can show that every matrix is similar to a matrix in this Jordan canonical form. Okay. And you can actually push these applications to differential equation also to include this Jordan canonical form. I think I don't have time to get to it, but you can read in books, and I think one of the books that I have seen which has a reasonably good account is a book on differential equation by somebody called Perko.